Hello again. Hope that everybody is well. Okay, so what I want to do today is to talk about the material chapter 5. I'm going to start by reviewing some material on normal distribution, and then we'll go on to do some of the things that we know how to do now, confidence intervals and hypothesis tests, in the light of that review. So I'm working on chapter 5, and so if you have if you have access to the book, you may want to take that out. So first, just to start out, good news. The good news is that we've done the hard part. The hard part of the course is the ideas behind confidence intervals and hypothesis test. Once we have those ideas, the technicalities of dropping them into formulas and etc., that's not the part that gives people trouble. The part that gives people trouble is the ideas of confidence interval and the idea of hypothesis tests. And that's not to say you don't have to do any work, but that is to say that if you were saying to yourself, this course got hard, it did, and now I think it'll get a little bit more routine. A person will feel a little less like struggling and a little more like, yeah, I know I can do this. Okay, so here we are, continuous distribution, normal distribution. So we've seen this slide already. This is a normal distribution, or it's sometimes called a Gaussian distribution, or sometimes called a bell curve. And in particular, I remember showing folks this formula and saying, this is the formula for that curve. You, of course, are not required to know anything about this formula, except that at one point, soon, not too long from now, soon, I'm going to say to you, here, we're looking at a curve. I'll say to you sometime soon, we're looking at a curve that looks like a bell curve, but it isn't a bell curve. And the reason it isn't a bell curve is because it doesn't satisfy the formula. Do you remember the formula? Here's that formula I'm going to ask you to remember. So it's shaped like an umbrella in the middle and like a bowl on the two sides. And the spot where it changes from umbrella to bowl, that's one standard deviation. So that says mu plus sigma. Mu is the part right in the middle there, the high spot. So this is, again, a familiar graph that we've talked about an awful lot, never mind having seen the slides before. It's centered at centered at z equals mu, and it has the spread of this is given by standard deviation sigma, so that from here to here is a distance of 1 sigma. Okay. And this distribution is absolutely critical because of the central limit theorem that I'm going to remind you what the central limit theorem says again. But first, a little practice with normal curves. So IQ tests. It's been my experience that most folks either have not taken an IQ test, but at least have some idea what it's supposed to measure. It's supposed to measure somehow your cognitive ability, native cognitive ability. IQ tests are set up so that they're centered at 100 and so that they have a standard deviation of 15. So there is people with an IQ of 115. That's right about where the curve changes from umbrella to bowl. People who have an IQ of 130, they are 2 standard deviations away from the mean. And we've done in the class a number of times, we've talked about how 2 standard deviations is some kind of back of the envelope idea of starting to get unusual. So people who have an IQ above 130 are starting to get unusual. People who have an IQ below 70, that's 2 standard deviations below the mean. People who have an IQ below 70 are starting to get unusual. So in fact, we have a pretty good idea of what those numbers are. If you take the left area below 70 and the right area above 130, in total that makes 5%, because the middle is 95, so the outsides must be 5. Since the outsides in total are 5%, the upper must be 2.5 and the lower must be 2.5. So in fact, if you have an IQ above 130, you're seeing something like 2.5% of the population. This is a standard normal curve, a particular example where the high spot is, the middle, mu, is 0, and where 1 standard deviation unit is 1, and we'll be seeing that on stat key pretty soon. I'm just, again, reminding you of some of the formulas, and this is one of the formulas that we will need to be using in order to work with the standard normal curve. Do you remember how you figure out how many standard deviation units a score is? So let's take, for example, a person who has an IQ score of 135. If they have an IQ score of 135, then you're going to take 135 for X 100 for mu, because that's what mu is for an IQ test, 15 for sigma. And you just calculate 135 minus 100 divided by 15, and then that number will be their standardized score. Their standardized score, or a person might say that's their z-score. A person might say that they are this many standard deviation units from the mean, that kind of stuff. Okay, so again, stuff that we've seen before, but just trying to remind a person how it goes. Most folks these days seem not to have had personal experience with IQ tests, but they do seem to have personal experience, it seems to me, with SAT tests. So just to give a person a second example, the middle is 500, mu is 500. Sigma, standard deviation, is 100. So people who get a 600 on, say, the math, SAT, are one standard deviation units above the mean. Their z-score is 1.00. If you get a 700 on the math SAT, you are 2 standard deviation units above the mean, and you are starting to get on the unusually high zone. So only about 2.5% of people get that high. If you're at 750, 780, 790, or 800, 800 is 3 standard deviation units above the mean. And the SAT company, just with the College Board, their name is, they figure they're just not going to bother to score people that high. They can't distinguish between an 800 and an 810 is the way they figure. And anyway, what difference does it make? So we use this test to try to figure out where people lie on that scale. It's the middle is 500 and standard deviation is 100, and it's just a matter of convenience. Okay, so for example, we can do a calculation. What's the chance of an SAT score less than 600? So let me bring up my paper and bring down the slides. SAT score less than 600. So let's see here. If you get x equals 600, okay, then your z-score is 600 minus 500 over 100. And the 600 that's your score. The 500 is mu, the middle of the SATs, and the 100 is sigma, the standard deviation of the SATs. So of course, this is 1.00. We would say that your z-score is 1.00. What percentage of people get a 1.00 or below? Okay, well, we'll ask StatKey that question. So let's see. I'll get rid of that, and I'll bring up StatKey if I can find the darn thing. There, I think that's it. Oh, I told you to go away. Why did you not go away? And go away. Okay, there we go. So now we have StatKey, and we want to ask what's the chance of a z-score of 1.00 or less. So on StatKey, I'm clicking on normal because this is a normal curve theoretical distribution. It says normal curve. StatKey comes up, not too bad. I want to ask it what's the chance of a 1.00 or less. So 1.0 or less is a left tail. So left tail, and it comes up with some default because it's got to come up somewhere. So I'll change that to say 1.00. 1.00. And there we go, 1.00 or less, quite clearly colored in. I don't know why on the slides I'm making it comes out in blue, but when you do it on your computer it comes out in red. I'm sorry, I don't know why. But it doesn't seem to make any difference. The point is that 0.841, about 84% of people get a 600 or less on the math SAT. Okay, so StatKey can tell us less, can tell us above, that all those kinds of answers that you want. Okay, let me bring StatKey down now, and oops, and back up to the slides, and so we can answer all these kind of questions, and we've had practice in the past answering all these questions, and in particular StatKey just loves to answer this kind of question. So, oops, I didn't, there we go. There we go. So I'll click past those questions, and we've done all of these in class before, so we know how to do all of these. Same thing with women heights. The point I wanted to make in this slide, and again we've talked about this before, but the point I wanted to make in this slide is that we talked about that 95% of the sample data lies within 2 standard deviation units of the mean. So if you take this graph and color in from -2 to +2, that you'll get 95%. That's not 100% true. That's why it says we lied. That's not 100% true. In fact, if you color in this and this, it doesn't say 95. It says 96. You know, good enough for practical people. But anyway, so 95 95% is actually 1.960, not 2, 1.960. You know, when we were trying to learn about 95% confidence intervals, the difference between 1.960 and 2 was not very important. So we didn't worry about it. But in fact, all those times we were saying 2, we really were, some of us were really thinking 1.960. So technically speaking, it's not 2, it's 1.960. But with this picture here, we could change to find not the 95% in the middle, but instead to find, say, 99% in the middle, or to find 90% in the middle, and do confidence intervals that are not just 95% confidence intervals, but also 99% confidence intervals, and 90% confidence intervals, and 99.999%. If you could go crazy. Now, we're not going to go crazy. We won't ever need an 87% confidence interval. But we do often use 90%, 95%, and 99. So what we will use in class, almost always the numbers are among these three, are 1.645 is associated, instead of 2, is associated with a 90% confidence interval. 1.960, and sometimes when we're being sloppy, we'll say 2. But when we have a calculator and you might as well punch the right number, we'll punch 1.960. And then finally, for a 99% confidence interval, we'll say 2.576. And so these are the numbers that we'll use in place of where in Chapter 4 we were writing 2 times the standard error. Here we'll write these 3 numbers. Okay. I'm going to skip over stay nines because you know, we're in an unusual circumstance with the virus situation, and I'm just leaving some things out, and stay nines is one of the things I'm leaving out. And then finally, to remind you of what the central limit theorem is. We started out with the paper bag experiment. I had pieces of paper in the bag that said either 1, 2, 3, 4, or 5, and how many there were in the bag. There was either 1 with a 1. There were 2 pieces of paper named 2, and etc. And each person drew a sample with 5 pieces of paper, and each reported their X bar. And when we got a sampling distribution, the sampling distribution did not look like this. So the sampling distribution doesn't look like the population. What a sampling distribution looks like is it looks like a bell curve. It looks like a normal curve. That sampling distribution does not look like the underlying distribution. It does, however, have the same center as the underlying distribution. So it's not unrelated, of course, but it doesn't look much like it. So the shape of the sampling distribution is not the shape of the underlying distribution. The mean of the sampling distribution is the same as the mean of the underlying distribution. Okay, and that's the central limit theorem. That's one of the big ideas of the course, one of the big ideas of mathematics, is no matter what is the underlying population, no matter what, whether it looks like so, or it doesn't matter, no matter what is the underlying population, the sample X bars are going to be normally distributed, or the sample P hats. The samples are going to be normally distributed. Okay, so the central limit theorem says, irrespective of how the population looks, the samples have to look normal. So when you see a bell curve in lots of places, this theorem helps to explain why you see bell curves in lots of places, because they're often averages of things. So specifically, the sampling distribution is got to be normal if the underlying population has a mean of mu and a standard deviation of sigma. Then the sampling distribution is going to have a mean of mu, same number, and the standard deviation of the sampling distribution is going to be sigma over square root of n. So if the underlying population has a mean of 12 and a standard deviation of 4, and you take samples of, samples of size 10, then the sampling distribution will have a mean of 12. It'll be centered on 12. And the standard deviation will be, what did I say, 4 over square root of did I say samples of size 10 for square root of 10? Okay. So here's one too many buttons. Here's an example. Suppose that if we could take a census, the first year class would have a mean of 75.4 and a standard deviation of 6.9. Now, of course, we can't take a census, but suppose we could, then this would be mu and this would be sigma. So that's the underlying population. Instead of taking a census, we're going to take samples of size 15. And every one of us is going to, so each of the 30 people in the room are going to take their own sample of size 15, and each of them is going to report their average. My X bar was, my X bar was, my X bars. How are these sample averages distributed? And then what percentage of the samples come out to be 80 or more? So let me bring up the piece of paper again. And let's have a look. So the SMC first year class has a mean of 75 and a standard deviation of 6.9. 75.4 and a standard deviation of 6.9. Okay, fair enough. Now we don't know that because we don't, that we wouldn't be doing a statistical study if we knew that, but nonetheless that's the actual fact. So the question is, what's the sampling distribution? Take samples of size 15, and you're going to get a bell curve. We saw this so many times when we were doing the bootstrap distributions. So there's so many times you're going to get a bell curve. What's its middle and what's its spreadedness? Okay, well the middle is going to be the same middle. The middle is going to be 75.4. So this is the sampling distribution. The distribution of X bars, the sampling distribution. So the middle is 75.4, same number, same number. What's the story with the spreadedness? So the spreadedness is going to be sigma over square root of n. So that's going to be 6.9 over square root of 15. And I don't know what my calculator says for 6.9 over square root of 15. Who can remember these things? Well, let's see. Square root of 15 equals, put it on the bottom of a fraction, and multiply by 6.9. And I got 1.78. So I got 1.78. Okay? Okay, so here we are back again, and we figured out how are the samples distributed. And we can ask questions like, what's the chance of being 80 or more? So I'm going to say here, what the sample averages are distributed in the way we just calculated. What percentage of the samples come out to be 80 or more? So of course I got to ask Stacky that question. So here we go back to the piece of paper. So where is 80 on that? Where is 80 on that curve? So we're going to do z equals x minus mu over sigma. So z equals 80 minus 75.4, because it says the samples have a middle of 75.4 all over 1.78. And of course I don't know what that is. Let's ask my calculator what it is. So 80 minus 75.4 equals, and divided by 1.78 equals, and I got 2.58 standard deviation units. So 2.58 standard deviation units, 2.58 standard deviation units, and I'm going to ask Stacky what that is. Let me see if I can find stat key down here. Stat key and get rid of what I already got. Okay. So stat key, here we go. What do I want? 2.58. So now I want to get rid of that left tail. And I want a right tail, 2.58. I don't want 1.960, I want 2.58. 2.58. And there, it says 0049. So that's not 5%. That's 0.5%. So that's quite a small number. That red area is quite small. So actually only a very small sample is that small. Okay? Okay, let's see. Bring me back to my thing. of stat key and back up to the slides. Oops. Suppose you were able to do a census of every person in the country, rating the president 1 to 10. Then we would find it shows the population average with a 3.1 with a population standard deviation of 0.6. And the problem is going to say, if they take a sample of size 25 and report our X bars, how will the sample be distributed? What's the chance of any one of us reporting a sample X bar between 3.2 and 3.3? Excuse me, between 3.2 and 3.3. Okay, fair enough. So let's try it. Okay, pieces of paper. It says that if we do a census of the country, then the average would be 3.1. So average of 3.1. There we go. A little better. So so mu equals 3.1 in the population. And in the population, the standard deviation of the population is 0.6. Okay, both of these are in the population. So now we take samples of n equals 25. And report the X bars. So what's the sampling distribution? Okay, well, the sampling distribution has to be a bell curve. It's got a middle. The middle is the same. The middle over here was 3.1, so the middle here has to be 3.1. The spreadedness is different, though. The spreadedness is going to be smaller. The spreadedness is going to be 0.6 over the square root of 25. So my calculator will tell me what that is. Square root of 25 is 5, of course. So 0.6 divided by 5, and my calculator tells me the answer is 0.12. So the sampling distribution is going to have a middle of 3.1 and a spreadedness of 0.12. Now it says, what's the chance that we report an X bar between 3.2 and 3.3? So I'll figure out what is the z-score for 3.2 and 3.3. 3.2 minus 3.1 over 0.12. Figure that out in a second. And then 3.3 minus 3.1 over 0.12. Okay, so this of course is 0.1 over 0.12. So 0.1 divided by 0.12, and I get 0.83. And then this is 0.2 over 0.12. 0.2 divided by 0.12. And I get 1.67. So I just have to ask stat key, what's the area between 1.67 and 0.83? So okay, so I'll go and ask stat key that question. Get rid of this. Oops, hit the wrong button. Get rid of this and get back to stat key. Stat key. Okay, stat key. What's the area between 0.83, which is about there, and 1.67. 1.67. Okay, so I want that to be 1.67. 1.67. It tells me that the red area is 0.47, and then I want this one to be 0.83. 0.83. Okay, and it tells me the three areas. On the left is 0.797, in the middle is 0.156, and on the upper is 0.047. I want the middle, so the answer to this question is about 16%, 15.5 or 16%. This area here is about 16%. Okay. Okay, one more question I think on the central limit theorem, and that is I want to do a hypothesis test question. Okay, so let me bring stat key down, and back up to the slides. Okay. So we know the ideas of hypothesis test, so applying them in a given circumstance is going to be much, much easier. Okay. So I'm asking about a test that our high school uh, our high school wants to give people the global inventory test, and we place a big high importance on globalism and geography. So we buy a test from a vendor, and the vendor tells us this test nationwide has a mean of 1,000 and a standard deviation of 100. So nationwide, they told us that. We think, of course, we place a lot of emphasis on globalism and geography, that our students will do better than the average bear. So we're going to take a sample of size 25, report an X bar, and hope that we provide evidence, strong evidence, that HA is right. That our students, that's what mu means in this question, our students, not every student who ever took the test, our students average better than 1,000. We don't know what the number is. Just because we reported 1070 doesn't mean we think our average is 1070. But we think 1070 might provide good evidence to reject H naught and say that for the average of our students is bigger than 1,000. Okay, so in order to figure that out, of course, exactly what I have to do is I have to figure out how far out is 1070 on the sampling distribution. All right, so here we go. So how far out is 1070 on the sampling distribution? So we say here, assume H naught, as we always do. Then the distribution of samples is, the central limit theorem says it has to be normal. The central limit theorem says it has to be the same as the distribution of the population. H naught thinks that that's 1,000. Okay, fine, 1,000. And H naught thinks that the standard deviation should be 100. So the standard deviation of the samples should be 100 over the square root of 25, because our sample has size 25. So that's 100 over 5, so that's 20. So this is the distribution of samples. This is what H naught thinks the distribution of X bars is. We ask, how far out is our sample? How far out is our X bar 1070? And we know that if it's so far out that it has a very small probability of happening, if it's way the heck out here, if it's so far out that it has a very small probability of happening, let's say if there's a small p-value, we'll reject H naught. So let's try it. So you calculate Z equals 1070 minus 1000 divided by 20, and you come up with a number. So that's 70 divided by 20 equals, says 3.5, and I'll ask stat key, how far out is a 3.5? So let's see, stat key, where are you there? There we go. Oh, that's the slides. Where's stat key? All the way down here at the bottom. Ah, there we go. I got to get rid of the slides. Too many darn things. Okay, so I'm going to ask stat key, how far out is a 3.5? Let me get rid of all this stuff, Okay, I want a right tail, and I want to make this say not 1.6, I want 3.5. 3.5, good. Oh, look at that. It's practically impossible. 3.5 doesn't happen. Well, that's not 1/10. That's 2/100ths of 1%. So the p-value is incredibly small. The p-value is 0.00023. Okay, so basically not happening. P-value is 0.00023. No, one too many O's. I'm sorry. 0.023. So these people are trying to claim that you did an experiment that had this chance of happening. So they're going to say to you, look, what I tried to claim seems like it is not right. So I'm starting to think HA might be right. So we reject H naught. Okay. Okay, very good. So once again, now the overall lesson is that we're in a position now where we are very good at the concepts behind things like hypothesis tests and confidence intervals. The calculation of them is usually not something that gives a person too much trouble. And so we're moving forward. This is chapter 5. We're moving forward, chapter 5 and 6. It will turn out to be actually downhill. Not easy, not a gravy boat, but actually downhill compared to the earlier chapters, just because you have to learn the hard part in order to do the later stuff. But the later stuff isn't the hard part. Okay, so very good. So what we find is that I'm asking you to do some, okay, let's get rid of that, asking you to do some homeworks. And this piece of paper is on Canvas. But anyway, just to bring it up, I'm going to ask you to do the homework for section 5.1 and section 5.2. I'm going to put up a video of me going over some of these homework questions, but of course, if you have homework questions, I hope that you will not hesitate to send an email or to visit me during my office hours, Monday, Wednesday, Friday at 1 o'clock at the Zoom address that I sent in an announcement, or find some other way to contact me with questions. Please do not hesitate. Okay. All right. I hope everybody is staying well, and we will see you next time.